Hello, this is the next video in a playlist that I'm calling hypothesis testing. And here we're looking at two-sided, uniformly most powerful, unbiased tests. And we're going to be in the Poisson setting. And you need to watch a video called Unbiased Hypothesis Test in this playlist. And that's where we discuss the theorem that we're using for this test to develop the test. So as an example, let's let y equal Poisson distribution with lambda, the parameter. I equals 1 to n, so we're taking a sample size of n. We're going to conduct an alpha level test with the null hypothesis lambda equal to lambda naught. So this is some value. Like in the example we use, I think we use 2 versus the alternative that it's not equal to lambda naught. So the distribution of our data is Poisson. And if we can rearrange that to look like this, I mean, it's essentially the same, of course, but this is a function of only the parameter, this is a function of only the data, and this is a function of the data and the parameter, right? And it's, raised to the e. Then this, it can be written like this, where just lambda, natural log of lambda we just call tau. And then the test function, it becomes the sum of those xi's, and we'll call it y. And the sum of independent Poissons is a Poisson with parameter n lambda, so y is distributed with n lambda. Note that the natural log of lambda is a one-to-one function of lambda. And lambda is strictly greater than 0. You can back solve for lambda, so lambda would be equal to e to the raised to the tau. And so since they're all one-to-one functions of each other, a test for tau or lambda are 100% equivalent. So according to the theorem in this video, the uniformly most powerful unbiased test is given by this test function phi. It's a function of our data. It equals 1 which means we reject the null hypothesis if y is less than some C1 or greater than some C2. We reject the null hypothesis with probability gamma 1 if y is equal to C1. The test function is gamma 2 if y is equal to C2. It's 0, meaning we do not reject if y is between C1 and C2. Where C1, C2, gamma 1, gamma 2 are determined by these two equations. Right, it's the expected value of our test function equal to alpha, and then it's the expected value of y times our test function equal to alpha times the expected value of y. You set these equations up, and then you just solve for C1, C2, gamma 1, and gamma 2. And so let's go through that process. Now, once we develop the two equations, it's actually pretty tough to do it by hand. But I write an R program that does it, in a split second. But you have to know what to program, and that's what we're getting ready to do here. So the first one, alpha equal to this expected value of the test function. So since it's discrete with 4 values, it's the value that it can assume times the probability of assuming that value. So it's 1 times the probability of that happening, which is this. Gamma 1 times the probability that y is equal to C1. Gamma 2 times the probability that y is equal to C2. Well, this is C1. Now, each time we're assuming that the true lambda parameter is the null hypothesized value, lambda naught. Now, we subtract these to the other side. That's what we get here. And then, this comes down. What we're doing is we're going to call this K1 in the program, the next video, this piece K2, and then K3. And so what I do is I cycle through all reasonable C1 and C2 values. And so I create a matrix of, tuples of C1 and C2. Then I solve for gamma 1 and gamma 2 that makes this alpha. And then this equation creates, a much smaller list, because gamma 1 and gamma 2 have to be between 0 and 1, right? It's a test function. And then, of course, with then the requirement of the second condition, it just instantly isolates the unique gamma 1 and gamma 2. So now let's look at this second equation. So we have lambda, the expected value of y, since it's Poisson, is just the parameter, which is in lambda naught. And then this is y times the test function. So it's y times each of those, and then times the probability of assuming those. So it's y times the probability of assuming that, which is this piece. Y times 1 is just y. So that's the y, and that's the Poisson, and the probability is summed. This is the second one, so it's y times that Poisson probability of C2. That's this piece right here. Then it's C1, right? We're at gamma 1, so y has to be C, right? So that y is C1. And then gamma 1, then times the probability of it happening, so you plug in C1 there. And then the same thing for C2. Now, what we do here is notice that this y cancels with one of the y's in y factorial. And note that when y is 0, this is 0, so it doesn't even, you might as well start at y1. The y cancels with one of those, and actually we take out one of these to make this y minus 1, which is the same as this. We do that same trick for this one. We bring out an in lambda naught, so it's y minus 1. You know, that y cancels with one of those, leaving this. And then we do the same trick here. You know, one of the C1s cancels with one of these. We get this, and we get this. And we have to factor out one of those, factor out one of these. Now look here. So the in lambda naught, so we get cancelizations everywhere, and we're left with this. But then what we do is we re-index it. We call y minus 1 w in each of these cases. And this would be, you know, w. Anyway, so on the back, we re-index it on the back page, and we let y equal 1, and then we end up with these probabilities. So it w, the new random variable, probability is left than C1 minus 1. That's that first equation. And maybe I'll reflash it, but that's what this is. That turns into this. Then the second piece I'll show you, third and fourth. So that's what we get here, here, and here. Now we subtract this and this to the other side. Oh, and w is now, you know, it's a Poisson in lambda. But these probabilities are a little bit different than the first equation. So we call this K4, K5, K6. And so since we've cycled through all the possible C1 and C2 tuples, you know, solving for two equations, two unknowns is really a straightforward thing. And so what I did here is I tried to create two equations, two unknowns, and then we'll use the R software to solve it. That's the next video. But there's an approach that is more commonly used, and it's called the equal tells approach. And here, the first equation, you know, instead of, you know, we ignore the second equation and we just make each tell equal to alpha over 2. So we find the C1 value such that being, you know, this randomized test being below is alpha over 2, and this is alpha over 2, which is this condition. This is equal to alpha over 2, and this is equal to alpha over 2. So it's an alpha level test, but it's only approximately uniformly most powerful unbiased test, and it's, you know, for large N. But it's much, much easier to find C1 and C2 and gamma 1 and gamma 2. In this approach, you can use the back of a book, you know, a chi-square table to find it. Where the first condition, you have to use a program or something to solve it. So, but it's only approximate. And so it's not unbiased. And what does that mean? It says when we're in the alternative region, the power function dips below alpha. And you'll see that in the graphical illustration in the next video. So here's the test, and if you want to try to recreate these numbers on your own before you watch the next video, We do an alpha level test, sample size of 25. The null hypothesis is lambda is equal to 2 versus that it's not equal to 2. The uniformly most powerful unbiased test is this condition. C1 and C2 are determined, alpha 1 and alpha 2. Now the Equatel test is the C1's the same, but the C2 is different, and then that generates different, gamma 1 and gamma 2s, and these are the tests. Now I would say probably this second condition is used so much more in practice, but now with computers I don't see why people don't use this first one more. Alright, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.